Hello, everyone. Welcome to the AI Hardware track of ValleyML AI Conference 2022. I'm Pratik Sharma. I'm a design engineer at ON Semiconductor, and I'll be co-chairing the AI Hardware track along with Moto Ikihashi from Intel. We have several interesting talks lined up for today. Let's begin by thanking our sponsors. Our platinum sponsors are Habana. The gold sponsors are Phoenix, Edge Impulse, and Cogni Fiber. And our silver sponsors are Applied Brain Research and Verda. Few housekeeping items. Please submit your questions through the Who Ask Q&A feature. You can submit your questions anytime during the session, and we'll get to them after the pre-recording ends. You need to scroll down to the bottom of the page to press the button to enter the live Q&A session. Next up, we have Dr. Chris Eliasmith. Chris is a co-founder and co-CEO of Applied Brain Research. Chris leads all of the scientific and technical aspects of Applied Brain Research. Chris is also a professor at the University of Waterloo, appointed in the Philosophy and Systems Design Engineering departments, and cross-appointed to the Computer Science. He holds the Canada Research Chair in Theoretical Neuroscience and is the director of the Center for Theoretical Neuroscience at the University of Waterloo. Chris has published over 100 articles and 2 books, How to Build a Brain and his seminal Neural Engineering. In 2015, he won the prestigious NSERC Polanyi Award for his research. Today, Chris is going to present an optimal time series processor using their Legendre Memory Unit.
Hi, my name is Chris Eliasmith. I am co-CEO of Applied Brain Research and a professor at the University of Waterloo. And today I want to talk about a piece of hardware that we're developing at ABR, which is an optimal time series processor. The problem we're trying to solve with this hardware is that people really want to start running more functional AI models at the edge. And right now, those models are essentially stuck in the cloud. The models that we're thinking of are the kinds that can do full speech recognition, lots of natural language processing for things like dialogue systems, or many other kinds of complex signal processing, might be things like arrhythmia detection, anomaly detection, and so on. Right now, the kinds of devices that people would like to put these in can't really afford expensive or power-hungry hardware that's currently available, things like CPUs and GPUs, or similarly can't afford constant connectivity, that is having to run things in the cloud and pay the bills for running those larger models to cloud service providers. Right now, they can afford these smaller pieces of hardware like microprocessors, but those only run small models because they don't have a lot of resources for or sufficient resources for running the large sorts of models that provide the functionality that people and device makers are interested in. So really, the quality that you get out of these small devices is quite low from an AI perspective. There are many use cases for this kind of ability. As I mentioned, things like arrhythmia detection and anomaly detection. So any kind of IoT device or sensor maker where they really want more sophisticated, larger AI models, which we kind of know from experience, the bigger your model, the better the functionality is likely to be. You can imagine for things like consumer electronics, say a camera, that you could essentially have a dialogue system which would just include the entire user manual in the device. So you could ask the camera, how do I change the autofocus or turn the autofocus off? And it would just be able to tell you that, instead of trying to either go online and search it up or go through a whole bunch of menus on the device itself. Similarly, for things like home robotics, et cetera, as soon as it's disconnected and you want to control it, a voice interface, for instance, is extremely natural. As well, consumers are becoming used to the kinds of voice interfaces that you get from having cloud-based language models and speech recognition, but they would prefer privacy. So they definitely like it when you don't send all of their data to the cloud. They want those responses to be fast, and you can get much faster and, in fact, lower cost if you put these things locally, as long as the hardware, of course, is appropriate. But being able to replicate exactly the kind of functionality that you would get from the cloud. So these are the kinds of things that people really want. This is, of course, what we have targeted our hardware to do. So the product that I'm talking about today is the time series processor from ABR. It has all the kinds of uses that I just covered, but we expect it to be less than $4 per chip, which is very good compared to a CPU or GPU able to perform similar kinds of functionality, which would cost on the order of $50. The energy envelope that we're looking at is also very low, on the order of about 25 milliwatts per chip running flat out. So this would let us do things like full speech recognition or complicated anomaly detection models. at extremely low powers. And overall, this will reduce, as you would expect, communication to the cloud, energy costs, which can definitely be important for anything that's running on a battery. And as I mentioned before, you get increased privacy and significant reductions in latency. Now, how are we going to do all this? It's actually not just a hardware design that's important here. Really, it comes down to the algorithm that this hardware is designed to run. This algorithm is our special sauce. It's called the Legendre Memory Unit. It's special in a number of ways. One is that, as you might know, for neural networks, it's extremely uncommon to be able to prove anything about their functionality. But in the case of the LMU, we can prove that it is optimal for compressing streaming time series data. And unsurprisingly, once you have that kind of advantage, if you apply it across many different benchmarks, it gives state-of-the-art results, as we've shown in many papers. These range from things like radio frequency classification to natural language processing, a whole variety of natural language processing, as well as sort of standard benchmarks like PSMNIST and so on. We've also compared it to all the standard techniques that people use to address those benchmarks, unsurprisingly, things like LSTMs, GRUs, CNNs, and of course, transformers, which are by far the most dominant in applications like ASR and NLP. And we show regularly that we do as well with fewer parameters. So we have significantly improved parameter efficiency. Often we get significantly better training efficiency as well, so much less data required to hit the same level of accuracy and so on. We have released a software package in Keras LMU, where people can actually use this technology. And what the hardware is basically taking that kind of algorithm and building a piece of hardware that can run it natively, giving us extremely high efficiencies. One thing that's interesting to point out about the LMU is its scaling. In particular, it scales constant time for memory, and with n, where n is the number of time series points that you look at before making your inference, in compute. So this is very good scaling compared to things like transformers, which scale n squared in both of those. And so as you can imagine, as your models get bigger and bigger, the advantages, in fact, increase for the LMU. So it's really the LMU that's allowing us to take these much typically larger kinds of models that would have to be run in the cloud and put them on a piece of affordable hardware. So what exactly is this optimization problem that we're solving? So the challenge really for dealing with streaming time series data can be broken down to essentially memorizing the information in the past that you want to use to make the inference now. So here we can see in gold, there's an input signal. In blue, there's an output signal. And really, the output is a delayed version of the input. Now, the challenge is that without any further constraints, this is actually an infinitely difficult problem. So if I haven't said anything about the frequency content of the signals, et cetera, then there could be an infinite amount of information you need to store during that delay before you put out the output signal. And what we've done for sort of mathematically speaking is demonstrate that for a given amount of resources, we can do as good as is possible for that number of resources to approximating this infinitely difficult problem. So really, that's where the optimization claim comes from. So putting this very briefly in mathematics, suppose that my output, y of t, is equal to my input, u, which is shifted by some amount of time theta. So pretend theta is 1 second. I get an input signal of some kind, and then 1 second later, I put that same signal out while constantly getting additional data. We can actually write this in the Laplace domain. And in the Laplace domain, where we have the input over the output, which is how you describe a transfer function, we see that it's equal to an irrational function, e to the negative theta s. And this is the reason I'm pointing this out is because this is basically where the proof of optimality can sort of get its teeth into. Specifically, what we're trying to do is say, okay, we know that we can't deal with an irrational function because it's going to have an infinite number of degrees of freedom. But what is the optimal finite version? So for some number of resources that we give it, which you can think of as neurons, so if we give it 6 neurons, what's the best we can possibly do for approximating that irrational function? And that is the kind of problem that you can solve mathematically. And once you do, you can then convert it into a form that looks very much like a neural network, which I have at the bottom, where A would be your recurrent connection matrix and B would be your input matrix. And those are really the two most important. And in fact, we can see that here. If you look at the diagram on the right-hand side, where we've drawn the Legendre Memory Unit in kind of the standard way that people draw recurrent neural networks, We have that linear core, which is the thing that we know is optimal. We have the input coming through that B matrix, and we have the recurrent connection, which is the sort of memory at the previous time step coming through the A connection. So with that core optimal linear memory, we can then put it through a nonlinearity, train it through backpropagation and so on, but we have this sort of basic advantage. So really the LMU is a recurrent neural network architecture, which optimally compresses temporal information. We can show from first principles that it is, optimal. And unsurprisingly, that leads to state-of-the-art performance and extreme parameter efficiency. And in fact, you don't have to train either the A matrix or the B matrix at all. And interestingly, as a bit of an aside, this actually explains a certain kind of cell that you see in the brain called a time cell, which I'm not going to go into. But we have formulated this as a continuous dynamical system, and that's essentially what lets us then treat it in all kinds of different ways. We can map it onto discrete hardware. We can look at how it would map onto continuous dynamical systems like the brain. We can also implement it with spiking neurons or not, and it's very robust to all these sort of different kinds of implementation. So specifically for performance, here's a couple of examples on natural language processing tasks compared to LSTMs. You can see the performance at the bottom where our LMU model is always better than the LSTM. And then I've listed the change in the number of parameters. And you can see it's 1 or 2 orders of magnitude more efficient, i.e. we're getting those accuracies with 1 or 2 orders of magnitude fewer parameters. Similarly, when we compare to a transformer, you can see that we're getting higher accuracy with about half the number of parameters. And in fact, we've shown in more recent work that this kind of scaling will remain as your transformer gets larger and larger. So the top 2 lines here are taken from a paper published by OpenAI in 2021. And they basically show the scaling of a standard transformer in green and an LSTM in red. And from this paper, they were basically arguing, look, you can see that the transformer is always better than the LSTM. We can then take that same graph and plot an LMU or a variant of the LMU where we add an attention layer. And you can see that we have now sort of improved over the transformer as much as the transformer improves over the LSTM. And as you might know, that improvement of the transformer of the LSTM resulted in the transformer just taking over essentially all of the natural language processing that's going on. I should mention this is for language models that we're looking at scaling. Another way of looking at this graph is that for a given level of accuracy in the transformer, if you want the same amount of accuracy for an LMU-based architecture, you can use about half the number of parameters. And of course, those are exactly the kinds of things that let us squish much bigger models onto edge hardware. And I would also mention that these advantages occur both during learning and inference. So the sort of architecture that we're mapping this onto is actually fairly straightforward. So in some ways, it's kind of boring, perhaps, from a hardware perspective. It's essentially in-memory compute with mostly memory. This chip is largely SRAM with a couple of CPUs for doing pre and post processing and so on. It's not going to be difficult to fabricate. Our expectation right now is that we're going to run it at a sort of medium scale node of about 22 nanometers, in which case it results in about a 5 by 5 die. We've done detailed cycle accurate power modeling for it, and that has allowed us to estimate the kind of power usage that we expect out of the fabric itself. The power numbers I was quoting before are for the entire chip, the entire SoC. We expect to have this chip in hand by Q4 of 2023, and that's after having consulted with a number of established production teams to get a good timeline for how long we think it will take to build this piece of hardware. The other thing I can mention is that we actually have a full software stack for this already. I mean, we're building the specific compiler for this chip, but we actually have a software stack called Nengo Edge, which you're more than welcome to check out at edge.nengo.ai, which allows you to essentially bring a data set, pick an architecture, and then hit optimize. You pick an architecture of your model, and you also pick a piece of hardware, hit optimize, and then it will take your data set, that architecture, and optimize it for that particular piece of hardware, and then allow you to run that model on the hardware in the cloud, so you can get latency and power information and so on. And so this entire stack, which is working for things like TPUs and microcontrollers and so on, is one that we will add basically this particular chip to. An example deployment, just to kind of get sort of to the meat of one of the what we think is going to be core use cases for the TSP, is essentially a dialogue system, right? So you have 2 chips, one of which is taking care of all of the speech recognition, another which is taking care of the natural language processing, and then you can use the sort of CPUs on core to do the dialogue management. And essentially that entire system we expect to cost less than $10 and run for about 50 milliwatts or less. And right now, to do that same kind of thing, you require a GPU, which is going to cost between $50 and $200. It's going to require a lot more memory. And that's, of course, because of things like the LMU optimizations. And those power budgets are typically on the order of about 10 watts. So as you can imagine, this is, we expect, going to open up a whole wide variety of applications which otherwise wouldn't be available if that kind of hardware with an LMU running on it, of course, wasn't available. Getting back to the market sizing, I don't think I'll spend too much time on this. As we all know, there are very large markets for all kinds of different edge compute. The particular slices that we're focused on are wherever you see time series. And so this is not only things like speech and so on, but also various wearable applications, IoT sorts of applications, sensors on vehicles that might need different kinds of processing, or if you're looking for patterns or wear and tear, et cetera, right? So all of the kinds of time series data that we find out there these days. And last but not least, none of this would have happened without a very capable team that we've got. We're sort of top heavy with PhDs, but right now we're doing a raise, and our expectation is that we're going to sort of fill in both the marketing and development teams to be able to finish what we've already started here as far as the chip design. And if anyone's interested in talking to us more about that, feel free to reach out. And thank you very much for your time. I look forward to your questions.
Thanks, Chris, for the great talk and for your insights in this time series processor. So let me start with a question. So do you have any current deployments or current applications for this processor?
Yeah, we definitely do. So we have 3 clients that we've built particular deployments for. 2 of them are in medical devices space, and 1 is automotive. And essentially the first one is where, we're not using our hardware, obviously, because the hardware is still in production, but we're taking that LMU and we're putting it on ARM processors, and we've, essentially we're doing cardiac detections or detecting heartbeats and then classifying them as being, okay, or having an arrhythmia or what have you. And so they had sort of used some in-house and off-the-shelf stuff that they worked with before, but they were running out of memory. And so we came along and we cranked up their accuracy by about 20%, I think, raw percentage accuracy, and we decreased, it was less than half of their original memory footprint. So it was a really nice example of demonstrating, how this sort of optimal algorithm can help even on contemporary hardware. So that was one. Another one was another medical device where they wanted basically doing speech interaction with the device. Same sort of thing, put it on already existing hardware, but made it much more accurate and efficient. And then the last one was really leveraging some of those results I showed near the end, where we can demonstrate that the LMU is significantly outperforming transformers. And so, we took a dialogue system and essentially replaced all of the transformers with LMUs, and again, showed that you have a nice decrease in latency and improvement in performance. And that one is sort of saying, look, we can take something that would have to run on a GPU, and it's going to cost a couple $100 to deploy, and put it all onto 2 chips. So it's kind of realizing that dialogue system that I talked about without the hardware yet, but basically showing the functionality and having a nice conversational system, which is very natural language oriented, easy to use, can kind of, it will respond robustly to strange ways of phrasing what you're interested in. So for instance, part of it was dealing with the environmental controls for the car. And so, somebody just went and said, my ass is cold. And it's like, I will, turn up your heat seater for you. Okay, we did not, intend for people to interact with it that way, but those kinds of language models really help it be robust.
Oh, that's interesting. So yeah, a lot of medical applications probably can benefit from time series processor like that, right?
Yeah, any signal processing at the edge, and medical devices definitely is a place where people are using that kind of technique a lot.
Yeah. So any thoughts on, like, in future, efficiency improvements in future with different AI hardware techniques?
Yeah, for sure. So I'm not sure how many people had a chance to see my talk yesterday. So I was talking yesterday about what can we learn from the brain style computing. And right now, our real focus for this hardware is getting it to market as fast as possible, because we really want to demonstrate its advantages. And we know they're there in virtue of the algorithm matching the hardware, or designing the hardware to natively implement that algorithm. But at the same time, in order to do that as quick as possible, we left off some more exotic features, I guess you could say. So things like event-based computing. And we know that that's going to even further improve the power envelopes that we're looking at now. But essentially, we figured we have enough of an advantage with what we've got on using regular techniques, that let's take that approach now, save things like event-based computing for subsequent designs or iterations of the chip. And then we've also been in conversations with people using sort of more exotic kinds of hardware techniques. ReRAM is pretty interesting to us right now. Our understanding is it's not really in the lower nodes yet. It's kind of up around 40 nanometers at this point, and we would probably like a little bit lower. But yeah, we've been working with researchers who have really been pushing that to try to, and working, I think they're working with global foundries too, the ones that we were talking to, really pushing that to try to get it into production. And so again, that's the kind of thing we will definitely consider down the road because of the power advantages there.
Yeah. Okay. I don't see any questions. So any important takeaways that you would like our listeners to have from this talk?
Sure. I mean, so many. I'll try not to repeat what the talk said. I think maybe what's helpful for the audience to hear is that some of the advantages that we think come along with our particular approach. One is, and this is maybe surprising to some, but is our software expertise. So like as a company, we've built software stacks for very exotic pieces of hardware, like analog digital neuromorphic hybrid chips, which are very strange to program. And so, we have to do a lot of work at making something which is usable by people who aren't us, right? So other people outside the lab or outside the company who are working in a lab, or even people who might just be familiar with things like TensorFlow. Like, how do you onboard those people to use your hardware? And we found that the software stack is really the critical thing. And so one of, I think, advantages that we've got here is that we actually have a software stack essentially ready to go, and all we need to do is attach a compiler for our new chip to it. So we built this stack that's called Nengo Edge. If anyone wants to check it out, you go to edge.nengo.ai. And it's set up right now so you can go in there, you can pick which hardware you want to target, you can pick which LMU architecture you want to use, and provide it with the data that you've got, or use data that's already there, and hit optimize. And then it goes through all of the optimizations, hardware aware training, quantization, that are targeted for each of those specific pieces of hardware. And then it will run it on the hardware in the cloud and give you all the data that you need. So it will tell you, what is the latency, what's the power usage, et cetera. And we think this is a great tool for people to compare with their data set across lots of different pieces of hardware. And it also provides an opportunity for us to just say, okay, our new chip is another piece of hardware we can put in that same stack. And so it really, it's basically just like using a SaaS tool, even though you're running it on the real hardware and getting back the real data. So we do hope that lowers the barrier to entry. People can try it out very quickly, see the advantages very fast, and essentially start working on their own deployments, as well as the ones that we're working on with larger clients.
Okay. All right. Thank you very much, Chris. It was very interesting. And
my pleasure.
All the audience for joining in. Bye.
Have a great day. Bye-bye.